Hello, good evening all. I hope you all can hear me and even hope you all can see my screen as well. So let me welcome you all to our session 13 for managerial economics, and even so this is going to be the second session for game theory, the topic we are involving. Now to move ahead, so since it's game theory, obviously, let me start from a game, because now you could remember the last session I mentioned, and even we discussed more, we'll say, like the notions, background, theories, rules, and a lot of ingredients of game theory. And today, the second session, we are going to apply them. Right? We are going to apply them and see how the outcomes would be. So then first let me start from a game, and then we'll move forward for game theory. So to start the game, what I will do, so I will flip my screen to my board, as we can use board to move forward with this game. Right, so I hope now you can see the board. So now even I will stop sharing screen so you can see board clearly now. And then first have system for this, I have a kind of reading for this game. So you all can see what you could see in this board. So here you have a matrix. So now we know, now when it's come to a game, obviously we have a matrix, right? Because from the last session, we learned this, we discussed this. Then, of course, here it's a game. And then once we have a game, so now even this game, which referring to game theory, so this is going to be a game, and then there we have a matrix, because this game is going to be a static game, because we learned 4 types of games with the last session, and this is a static game. So once we have a static game, typically we'll use a matrix like this, right? And I hope you all can see my screen in the wider screen. Is that true? Can you all see board clearly?
Yes, sir. Yes.
Okay, thanks. Right. So now this is the game, the matrix. And if it's a dynamic game, then it's not going to be a matrix, but we are not going to discuss that in this course, right? So we'll discuss that things in advanced courses like game theory for decision making and business strategy and so on. So then here, let me provide you a hint for this game, or how this game is going to be. So now basically you all familiar with, I guess, these 2 outcomes or possible actions, we'll say, right? And we'll say, so we have 2 players anyhow, player 2, and we'll say here we have player 1, and here player 1 got up, middle and down, player 2 got left, middle and right. So we'll say there are possible movements for them, right? So depending on the outcomes, payoffs, so we'll go for our decision, for our strategy, for our whatever utility maximization output we are desired because of these options available. So now we discussed them all yesterday, right? So then we'll directly move to the game, and then we'll discuss how we'll go forward with this game. So here, let me say this way. So now to start this game, first we'll start game from here. So this is our starting point. Okay. So we'll start game from here. So what is that? Middle for player 1 and left for player 2. So we'll start from combination NL, middle and left, right? So we'll start from here, and now what you have to do within this game, always the confront decision maker or the opposite player will go for the best option or best choice, because now here we discussed yesterday when it comes to game theory. So once we refer to these outcomes, always this what we call this rational decision makers going to optimize the outcome, right? So they are going to select the optimal outcome. They are always into optimizing their gain, optimizing their utility, optimizing their profits or whatever. So then here even this player is going to optimize his gain. And then how that will happen? So then now we have 2 outcomes. We know, we discussed yesterday, even before, especially with the last session we discussed that we have these 2 outcomes, and the first outcome, which is for which player? So usually is 5 for which player? So we have 2 players here.
Player 1, sir.
Yeah, 5 for player 1 and 4 for player 2. So the same thing applies for any combination in this matrix. Right? And then, so we'll start from here and we'll think first player 1 played his option here. So it means this decision because of player 1. It means player 1 stopped here. So when you start the game here, while thinking of 5 as the outcome. And now player 2 got the next chance to go for the decision. And player 2 will think of existing decision of player 1 and will try to maximize his or her outcome. What I said, so now player 1 starts the game here, and then player 2 now player 1 choose middle, and now player 2 should find his or her optimal outcome. So now then likewise you will go through a process, few steps. So this is the initial step, and step 2, then player 2 will optimize outcome, and then step 3 again player 1 will optimize because player 2 choose the destination and player 1 will optimize. Likewise, we'll go across 7 steps. That's the game. So now you need to move through the steps. So I will show you one step, for example, and then you have to lead myself towards the next 6 steps, right? So here at the initial point, player 1 chose the option middle because of 5 payouts, right? And then now player 2 got the chance for the next movement, and then player 2 now player 1 here with middle as the option, as the choice. So then what would be player 2's option? So once player 1 play middle, so then what's the best for player 2 once having player 1 play middle? Can someone mention? Once player 1 plays middle, what's the best for player 2?
4, sir.
4 means what? What's the best outcome for player 2? Knowing that player 1 plays middle. So
Low, sir.
Yes?
Low 1 L.
Is it L? So how will you look into player 2? So how did you recognize it as L? So then L means the same position, no? Player 1 chose middle, right? So player 1 selected middle, and knowing that player 2 should think of their choices. Now, how many choices player 2 got? 3 choices: left, middle, and right. So out of these 3, now player 2 player 1 plays middle, and then player 1 will not deviate to any other option here because that player played middle. And then knowing that, then player 2 have to select from these 3 options, isn't it? So this is going to be the possible options available for player 2. So player 2 got 3 options: this one, or this one. Because why? Player 1 almost played 1. I mean his action. That's middle. And having that, player 2 goes for his action or his or her action to optimize outcome. So then what's the best outcome for player 2 here?
R, sir.
Yes, of course. Because why? Player 2 will gain 5. Right? So then that's going to be the best outcome for player 2. So then, so what will happen here? Because of the best outcome for player 2 will move from here to here. Right? So then now we have this place. So this is our destination. And now player 1 should play his best option, knowing that player 2 end up with this position. So then what's going to be the next best option for player 1? Can you guess? Having this, what's going to be the next best option for player 1?
Upper level.
Upper level, okay. Why? Because now player 1 player 2 ends up with this. Right? Because player 1 got 3 options available: up, middle, or down. And as you correctly said, so the best outcome will be 5 if you go through this 3, and then it will be up R, U R, which is the strategic combination. right? Okay, so then if player 2 goes again, what will happen? If player 2 goes again, so then now player 2 no, player 1 ends up with up, and then player 2 got this, and then what's the best for player 2? It's going to be middle because it's 5 here. Higher the unit here, higher the utility of gain here. So if you think it that way, so this will be the best outcome, and then player 2 will end up with here, and then again player 1. Now player 1 will think, okay, so now player 2 end up here, and then I got these options, right? I got these options, and as I got these options, so then where are the best for me? So again, for player 1 got 3 options available: this one, and this one.
Down.
Best, yeah, of course, down. So player 1 end up with here, and then again player 2 has to go for the decision. So what's going to be the decision? So having or knowing that down going to be his player 1's destination, what's the best for player 2? Among this is going to be the best, and then we'll end up with D. Right? So we almost go across 7 steps, and once we go across 7 steps, we can see a pattern. Can you see a pattern there? What's the pattern? Start from here, goes like this, and goes like this. So we'll start from here, like you say, like okay, we start from here. So this is the pattern. What is the symbol?
Infinitive.
Infinity, of course. Infinity game, isn't it? So if you go across this all over, you are traveling across infinity, right? So now when it's called infinity sign, who's the person you can remember or you could remind? So we are moving across, or moving along a kind of infinity of combinations here. If you think of strategic decision making here, if we provide these two decision makers unlimited steps or unlimited approaches, they will always travel across this. Right? Will you remember the last video I showed you from John Nash? Right? So the John Nash video, if you could remember, started with infinity, the symbol, and he did his calculations on infinity of choices, because it's about human beings, it's about behavior, right? So now when it's come to game theory, we are studying behavior in human beings, not particles. So now earlier with that previous lesson, decision making on the uncertainty, we dealt with particles, some nature, maybe some situation, but here we are dealing with two human beings, two players, two rational decision makers, right? And once we have two rational decision makers, they got infinity of choices, because they may think different ways, right? Even we know from basic economics, we have this unlimited bonds, so on, so on, right? So we got infinity of things available, and it's really complex. And then anyhow, what John Nash attempted to make it in a proper stream, and to introduce this game theory to streamline their behavior and their interactions, and then to finally show a kind of equilibrium of their interactions. Now, when it comes to equilibria, we know we have different types of equilibria. Now, from basic economics, even from 100 level and towards from mainstream economics, we know we have this market equilibrium, and then later on we have a lot of other equilibriums, right? Now, even here in these games, even we are reaching towards an equilibrium, but which is totally different from the typical equilibria we see in neoclassical or whatever mainstream economics. Right? Here, this equilibrium is more psychological, which is more embedded to decisions. Right? Now, with that, let me go to another step. So I will move to the slides, and we'll come back to discuss another important thing. Now, so if we move forward, right, with this game theory and its applications, let me start with this example. Right? Now, I need your contribution, right? I need your interaction to move forward with this particular example given. So now here, you can see two person I mean, two individuals who are somewhere. So it looks like what? It looks like what? So can I say it's a prison? Like, so we have cages, and so then we have two shells of prisons, and we have two individuals who are in the prison, right? So let me say that. So we got two people who fought for, we say, a crime, and then both are suspected or suspects for this particular crime. And now police officers need to verify how this was happened, right? Police officers need to verify how this. Now now they got two individuals, and now what they are going to do, they are going to interview each prisoner separately. That's why they deliberately, purposely put these prisoners in two different shells, because now they cannot discuss. Even this thick wall will not allow them to murmur, even because it's not possible. We'll assume that, right? So they cannot discuss anything anyway while staying in two different cells. Now, first, police officer approached one prisoner and asked some questions about this crime, and then even this police officer approached the other prisoner later and also asked questions about this crime. Now, what police officer going to do? He is trying to recognize what exactly happened and who did it exactly. Because now we have two suspected, or two people who are the suspected for this problem, for this crime, but still we do not know exactly who did it. Now we need to confirm. So then first I will go into the blue shell as the police officer, and then I will ask questions like, who did it? Did you did it? So if you say you did it, so then there will be some outcomes. If you say no, so then there will be some outcome. So how we will ask it in this way? We will ask this prisoner, if you expect or if you confess that you did it, then your charge will be this much of years in jail. But if you not confess, if you not accept, so then it will be this much of years in jail, likewise, right? So then we'll offer this for both prisoners, and let me show you our offer in a matrix, right? So now as a police officer, I'm offering them these possible outcomes, right? I'm offering them these possible outcomes. Hope you can see. So each prisoner can confess or not confess. So confess means the prisoner can say, yes, I did it, or even prisoner can say, no, I didn't, that person, no, whatever, whoever did it, like this, right? Then now the outcome will be like this. If the particular prisoner confess, right, and the other one not confessed, and the prisoner who confessed will end up with 3 years in jail, and prisoner who not confessed will free to go. If both prisoners not confess, if both prisoners say no, I didn't, so both have to stay 1 year in the jail. If both prisoners confess, then both have to stay 2 years in the jail. That is what you can see in this matrix. Okay. Now we'll try to see what's going to be the best possible outcome for these prisoners. So where they will end up, it's not their decision, because now they can discuss now, but they can go for their own choice, and how their optimal choice will be. That is what we are going to discuss, right? Now for that, now we'll follow the same thing in the previous game. Just basically we did something like, we just try to see what's the best possible option for player once given the decision from another player, or once know the decision from another player, outcomes for the other players, right? Knowing that, so we'll see what will happen here, right? So we'll see what will happen here, and now can you basically think of possible decisions by each player, because even in the last session we discussed a bit about possible decisions based outcomes, and even can you think here what's going to be the possible best outcome for each player for the given situation? Till you think that, let me change the board, and there we'll discuss it. Till that you can think of this matrix. do it your own first. Try to see best possible outcomes for players at each situation or in each situation. So what do you think about their optimal decisions? Now first we think it in this way. First we got prisoner 1 and now knowing prisoner 2 will either go for confess or non-confess. Now prisoner 1 will look into his or her best outcome, right? Best option available. So prisoner 1, if prisoner 1 thinking of two choices, confess or non-confess, knowing that prisoner 2 got these two choices, again confess or non-confess, he will now go through these possible outcomes. Now these outcomes given in number of years in jail. Now here see, it's about number of years in jail. It means 1 means only 1 year in jail, 2 means 2 years in jail, 3 means 3 years in jail. Higher the number will worse your outcome. So think it in that way, right? Because initially it's really important to understand what the expression through this outcome. What's the expression given in this payoffs? So greater the payoffs will decrease your utility, will decrease your benefit. So you have to stay more years if greater the number in the jail. So then a person would happy to stay less years in the jail always, isn't it? Individual would happy to stay only less years rather greater number of years. So thinking in that way, if player 1 thinking of player 2, what will be the best option? If player 2 plays, or if player 2 says I will confess, in that case, what's the best option for player 1? If player 2 says to the police officer, sir, I am going to confess. So then what's the best option for player 1?
Non-confess.
Non-confess. Okay. What is that? Is it 0?
3, sir.
This one. Okay. Then if player plays in this way, right? If player 2 plays non-confess, what's the best for player 1?
Again, non-confess. 1.
Again non-confess. This one.
1, sir.
Here.
Next one, no, sir.
Which one?
The right one, sir. In 1, 1, the right one.
This one.
Yes.
101. So here this one. Is that? So how will analyze this? So you say 1 here. Is that?
So if player 2 choose this contrast, then there's a available alternatives 2 and 3 for player 1. So in that case, he can choose the 3 non-contrast. And also if the player 2 non-contrast, then again he has a alternative 0 and 1. So with that, he can go with the 1.
Okay. So then now, as you said, so we think it is this way, right? Now, if confess, now if player 2 confess, and what player 1 can do, right? So if player 1, player 2 confess, in which row we have to think of it? I mean, in which way we look into it? So now we'll think it this way, right? Let me say it in this way. So first we'll see player 1 got the chances, right? Player 1 got the chances. So if player 1 confess, what is the best for player 2?
3.
3. You mean from these options?
So we need to check it in the row wise, no, sir.
Okay, is this alright? Then how?
2 and 3 are possible alternatives. Then we can go with the 3.
Now we are thinking of player 2. If player 1 plays or player 1 says confess, and then for player 2,
Confess. 2.
2. Why 2?
Because when we look at player 1, for player 2, there are 2 and 0 are the alternative. Within that, 2 is a greater payoff.
Greater payoff. Okay. So what about then the other choice? If player 1 plays non-confess, then? What will happen?
Player 2 can confess because 3 and 1, within that we can choose 3.
Okay. So then if non-confess, player 2 will go for confess. You mean 3. Now earlier the decisions were on less number of payouts and now it's on higher. Why? Earlier preferred 0 and 1, thinking of less, and now going for greater payoff. Why that?
Excuse me, sir.
Yes, Sujal. Lakshan?
Sir, body single explanation is then what about like theory?
You need a kind of signal idea on this.
Yes, sir.
මෙතන වෙන්නේ දැන් මෙතන ක්‍රීඩක දෙන්නෙක් ඉන්නවා. හරි? අපිට මෙතන ඉන්නවා සිරකරු දෙන්නෙක්. දැන් මේ දෙන්නා හිරේ කතාව කරනවා නේද?
ඔව් ඒක තමයි.
හරි. ඊට පස්සේ මේ සිරකරු දෙන්නට ඔප්ෂන් දෙකක් තියෙනවා, choices දෙකක් තියෙනවා. එයාට කියන්න පුළුවන් හරි මම පිළිගන්නවා මම වැරද්ද කරා කියලා නැත්නම් මම පිළිගන්නේ නැහැ. දෙක දෙකක් කියන්න පුළුවන්. හරි? confess කියන්නේ පිළිගන්නවා කියනවා. වරද වාර ගන්නවා. not confess කියන්නේ වරද වාර ගන්නේ නැහැ කියන එක. හරි? දැන් මෙතන වැදගත්ම දේ මෙන්න මේ outcomes ටික define කරගන්න. මොකද මේක තමයි ගොඩක් වෙලාවට අපිට games වල ගොඩක් වෙලාවට අපි තීරණ වැරදෙන්න හේතු වෙන්නේ. right? අපි කියන පැටලෙන විශේෂයෙන් දැන් මෙතන දැක්කම පොඩ්ඩක් අපි ඒ කලින් අපි options එකේදී දීතුවනේ. දැන් ඇත්තට මොකක්ද මේවා කියන්නේ? මේවා කියන්නේ outcomes. වෙන බලන්න ප්‍රතිඵල. හරි? එතකොට දැන් මෙතන දැන් අපි ප්‍රතිඵලය කොහොමද ඩිෆයින් කරගන්නේ කියන එක මත අපේ ඩිසිෂන් එක වෙනස් වෙනවා. ඒතර අපි හරියට අපේ ප්‍රතිඵලය ඩිෆයින් කරගෙන ඉන්නවා. මොකක්ද මේ ප්‍රතිඵලය කියන්නේ කියන එක. හරිද? මේ මොකක්ද මේ ප්‍රතිඵලය කියන්නේ කියන එක. එතකොට මේකෙදී මේ 2 1 3 ඒ කියන්නේ අපි හිතමු හිරේ ඉන්න වෙන අවුරුදු ගාන කියලා. හිරේ ඉන්න වෙන අවුරුදු ගාන කියනකො. right? අපිට හිරේ ඉන්න වෙන අවුරුදු ගාන. එතකොට අපි බලනවා දැන් එහෙනම් දැන් වරදකට අහුවෙච්ච කෙනෙක් හිරේ ඉන්න කැමති අඩු අවුරුදු ගානක් නේ. එහෙනම් සාමාන්‍යයෙන් අපේ යුටිලිටි එක වැඩි කරගෙන නැත්නම් අපි ගන්න ගේන් එක වැඩි වෙන්නේ අපි අඩු අවුරුදු ගානක් මේ හිරේ ඉන්න පුළුවන් නම්. නැත්නම් හිරේ නිදාස් වෙන්න ඕන අපි කැමති කොහොමද? ඒක තමයි අයිඩියා. ඒක හිතාගෙන බලන්න ඕනේ කොහොමද මෙයාලා ඩිස්ටන්ස් වල යන්නේ කියලා. එතන ඒ වගේ අපි අර ස්ටැටික් ගේම් එකේ කතා කරා තොරතුරු සියල්ලම දීලා තියෙන්නේ. ඒකට අපි දන්නවා මේ අනිත් එක්කෙනාගේ choices මොනවද? ඒ වගේම outcomes මොනවද? payoffs මොනවද කියලා. ඒක දැනගෙන අපිට තියෙන්නේ ඉස්සරහට move වෙලා බලන්න හරි මට මේ අවස්ථාව ලැබුණොත් මම මොකක්ද දෙන හොඳම උත්තරය? මොකක්ද මගෙන් යන හොඳම outcome එක? මම ගන්න decision එක. Right? So think it in that way. Okay?
Okay.
Lakshan, there are.
Oh, sir. Thank you.
Right. So then, what could be your desired choice?
Sir,
Yes,
both can go with the contrast. Is it correct, sir?
both can go with the confess.
Yes, sir.
Why? Why both will go with confess?
So when player one go with the contrast, then player two can go with the contrast as well. Then he got 2 and 0, then 2. Then we can go likewise. Then when player two choose this option, we can see in that section wise. Then we can say the column wise. If it be so like that, then when player two confer. What is the name for that? If we sometimes if we take C, then play one can also go with this C.
Okay, confess.
Yeah, can plus, yes.
Okay, right. So why it happens so that now, so we'll compare the argument with the possible other outcome, possible other players, right? Now, player 2 choosing 2 here because of why then, according to you? Because player 2 got 2 choices, either 2 or 3, isn't it? 2 or 3. If player 1 goes for confess, and when he goes for confess, it will be 2, and here it will be 3. Right? And then anyhow, 2 will be greater than, I mean better than, sorry, not greater obviously, better than 3 numbers or greater than 3 in terms of the game outcome. And here, now if you think of the player 2, will compare between 2 and 3. And then again, the same thing applies, end up with 2. Right? And then the rest, or the other way around also, there should be some distance now. Now, with non-confess, what are the options available? 0 and 1, 3 and 1. So with 0 and 1, 0 will be good. With 3 and 1 for player 2, 1 will be good. And then finally, in this outcome matrix, finally, they will end up with this option, confess and confess. Right. So do not worry, maybe now you feel this bit confused as we initially start with this prisoner's dilemma, because it's itself says dilemma, you may see the topic, right? Because I thought of starting from dilemma, if we start from the dilemma, obviously we can go for clear discussions later on, right? Because now once we confuse first, it's better. Because once we confuse first, and then now later we can relax this complexity, relax this problem while referring to John Nash, and then we can see why we are having such complexities. Now, so far, let me state that confess and confess going to be the outcome, optimal outcome, though they got a chance to stay only 1 year each in the jail as well, right? But finally end up with 2 years in jail. Now, so I'm going to provide a material to you, reading material. I will show that even to you. So in that material, you have this story in a nice way, and later you can go through that story and read it. It's a kind of graphic book that will support you to learn game theory nicely. And from that book you can read it further, and you can get to know what exactly going on. Right. So I will upload that book into the Moodle soon after, after the lecture, and then you can have it and read the prisoner's dilemma in that book as well. It's a kind of story given you, and that will explain you nicely after the session why exactly they end up with this decision. Right? Okay. So with that, we'll move ahead towards the rest of the content, and then we'll discuss obviously more examples and even more approaches to simplify the matrices and even to simplify the outcomes and decisions of players. So we'll start from the dilemma towards more simple, less complex things. So then it's good, isn't it? Rather going from simple to complex, better here in game theory, starting from complex and then relaxing towards simple versions, right? Okay, hope you can see the screen. So then it's about number of years in prison, and the PO strategy is going to be complex and continue of the outcome going to be. So we'll discuss this PO strategy and in the Nash equilibrium at the zone. Don't worry, because now we are going to discuss about John Nash now. Right? Now, how Nash recognized this? Now, when it's called John Nash, he recognized something like this. So first, let me say it in words, simple words, and we'll see a video as well. He identified that for individuals or for rational decision makers, their optimal choice is usually going to be the second best choice. Now, will you agree with this? Their optimal choice is usually going to be second best choice once they play with rivals, once they have to make the decision with some others, competing with others. This is what I mean, out of his findings, this is one of findings which say rational decision makers, I mean the individuals, will go for their second best choice in nature or in usual practices. Now, let me show you from the film Beautiful Mind how he recognized this matter. So we'll watch it first, and then we'll expand our discussion further and further as well. Right? Hope you can see the screen. So we'll watch it and we'll discuss.
Circling your papers for 5 seconds. Not by you, Joe. Here. Oh, we're not here for you. She want a large friend. Say sword, John. Pistols at home. Have you remembered nothing? All the lessons in Adam's father and mother. In competition, individual ambition serves the common good. Exactly. Every man for himself. Those who strike her are some of the friends. Later, bottom line, king. Let me look. Look over. Look at Ash. I can have you ever been out of the way to I was going to be traditional. What are you talking about? We don't come from the pond. We block each other. Not a single one of us to come get it. So then we go for the friends. They will all give us the cold shoulder because one of the last seven shores. But if no one goes for the line, don't get in each other's way. And we don't show their girls. So we win. Anyway, we all get later. Instead, best result comes. Everyone of you doing what's best for yourself, right? That's what he said. Best result comes. From everyone doing what's best for yourself. And the group. Action. This is somewhere for you to get the blood on your own. You can go to Go to Zion House, gentlemen. Go to Zion House. Absolutely.
Right. So according to film, that is how Nash got to know that there are the equilibrium and there is the second best choice for an individual. Right. So did you get it? The way it explains in that movie. So can someone say how you recognize it.
So we cannot hear the sounds that.
You didn't hear the sound clearly. Okay,
Yeah.
so then in that video, so later you can I will upload it even from YouTube. You can watch it. I mean, better if you can watch the whole movie. Even I mentioned it last session. So watch it all together, so that you will get a nice idea about John Nash and even about the game theory in a way. And what there was like now this person, this individual. I mean, initially when it's come to adjustment, this adjustment is concerned on like the individual rational decision makers will go for commonly optimize the outcomes and so on, right? So always they will think of common good, the best for all, and then so they all will try to maximize the outcome. But what John has recognized, no, once he given an option, if we have more rivals for that option, then they will not, obviously all will not going for that option, rather they will go for the second best choice, second option available. Right? So in that video, even there was a girl provided given, and then however the people not goes for that girl, rather they goes for the other girl, her friends and all. So it's that way he attempt to explain. So people are going for their second best choice rather than the competitive choice. So now from here we'll see how exactly he explained this, right? So here what he mentioned, the players will end up with different decisions, of course, right? However, there's an equilibrium when it comes to decision making. That is what Nash recognized. So how we recognize that decision equilibrium? Because now once we have players, now for example, you can think of two players, right? In a typical matrix. So players predict usually the other will play their best option. This is the first case, because I will predict, okay, my competitor will go for his or her best option, and then what I will think of my move, my decision, right? Now, anyhow, when it's come to an equilibrium, so in this Nash equilibrium, the people finally end up with this Nash equilibrium, and there are so many other incentive for these people to deviate from that equilibrium. So we got two features to say why there is no any other equilibrium, and why these non-Nash equilibrium strategies are not preferred by our players. So there are two terms that we call inconsistency and self-infirmity. Inconsistency means, I mean, any other option available for people away from this Nash equilibrium. So do not worry yet. So we'll come into Nash equilibrium, right? So by the next step, we'll see how we can reach the Nash equilibrium, and then how we can construct the Nash equilibrium, and then you will make it more clear. First, let me go through these words and these facts, and then we'll see with more rigorous, simple examples. So these choices are inconsistent. So if it is not Nash equilibrium, it is inconsistent. So if it is Nash equilibrium, so that equilibrium will be the choice for people, and that will not provide any incentive for the player, the decision maker, to deviate from the decision. So any other available strategies are inconsistent because of that. Even self-infirming. So self-infirming is a kind of weak. It has a kind of individual weakness when it comes to other decisions, right? As a result, so what you can see here, even if everyone predicts that this will be played, then someone has an incentive to deviate here. So then, if once we have other choices, non-Nash equilibrium strategies, them are inconsistent and self-infirming. It means them are not strong and them are not sustained, seems like, and then the others will go for some other choices, rather staying with the same choice, or getting together with the same choice, cooperating with the choice. As a result, the Nash equilibrium will be the only equilibrium, or only the type of equilibrium which is possible in a game, in a such decision making process. This is what Nash mentioned So obviously he proved this from a lot of mathematics, as initially he was a mathematician and then he joined or he applied things in the stream of economics and won Nobel in 1994 for his contribution for economics. And anyhow, now we'll try to look into this simply. Now we are going to break down this into simple facts and then recognize what exactly Nash saying here, what exactly Nash mentioned here. Right? So first we'll use an example with a normal form game. So I think you all know what is normal form game. It is another term for static games. So then we will use a static game for an example or a normal form game. The same thing. I mean, these all words for the same thing. So then we don't need to worry about that. And then what we'll do first, we'll characterize each agent's set of PO strategies. Now, even we discussed about this PO strategies last session. So then we know what means PO strategy, right? PO strategies are the choices available for any player, and the probability of each choice is going to be 1, right? And even we discussed about mixed strategies. So when it's called mixed strategies, probability less than 1, and combination of mixed strategies will give us the probability of 1. But now here, when it's called PO strategy, we got probability equals 1. It means it's complete in some decision, and they may got number of such complete decisions. Out of that, they will think of their own choice. And so then this is very important. So we need to characterize these players, these agents or these decision makers, PO strategies. So we'll do it soon. And then once we characterize it clearly, carefully, then we can identify Nash equilibrium. Right? And then even further we can study whether we have only one Nash equilibrium or whether we have more Nash equilibrium. So whether we have mixed strategy Nash equilibrium, so on, so on, so on, things will be complicated. Right. So this is the first example. So we got 2x3 matrix. So player 1 got 2 decisions up and down. Player 2 got 3 decisions left, middle, and right. Right. Even you can see payouts. Payouts given accordingly. Right. So now we are going to recognize their each choices. Right. We are going to recognize their choices. So now here, first we'll go with the player 1. What are the best strategy profiles for player 1? That is what we'll need first. Right. So let me get into board. Till that you can go through this and see what are the best strategy profiles, and then we'll discuss. Right. Okay. So we'll see. So let me enlarge the board for you. Right. So now this is the matrix. Okay. So first we go with player 1, and then later we'll arrive to player 2. So now what we look, what are the best strategies for player 1? Right. So this is a static game with complete information. Right. A static game with complete information. So then we know. So we have a matrix that will represent the static game and all information available. I mean the payouts and all. Right. And even the rational decision maker will maximize their utility while gaining higher number of utilities. So greater the number will greater their outcomes utility. So that's also there. So then now what's the best choice for player 1 for each attempt?
So when player 2 can choose middle, it is a better payoff because he can gain 2.
Okay, if player 1 plays up, player 2 will gain middle, as player 2 will get best here. Okay, right? And if player 1 plays down,
Low, player 2, low one, L.
which one?
3, sir, 3 payoff. At player 2 can go with the L.
L, okay, yes. Okay, simply now the way you recognize it depending on the size of the number. So then here, grade number 2, which is the greatest outcome. So you went there. Here number 3 is the greatest outcome out of these 3. So because we have to use this and this, and then this will be the greatest outcome for player 2. Once the player 1 plays D, and here even we got this, and this, and then player 2 goes for this as is the highest outcome. Right. Now we think of the other way. So once player 2 plays L,
U, upper
What?
level.
yes, U.
U, sir.
Okay. And then if player 2 plays middle,
Again U.
okay. And if player 2 plays right, R,
Down.
this one. Is it clear for everyone? So because what happened? So now we'll think once player 2 plays, if player 2 go for left, then player 1 will think, okay, so I can go either up and down. So then I am looking forward for my outcomes. 1 and 0 will be my outcome. This and this. And then the best will be this one. So goes for this. And once player 2 plays middle, so what are my outcomes? 1 and 0 are possible outcomes from up and down, and again 1 will be the best. And then once player 2 goes for right, and here 0 and 2 are my outcomes, possible outcomes, the best will be 2. Right. So them are the decisions, strategy profiles for these players in the given situation. Now, having this, see whether we have a strategic profile combination where both players prefer to go for. Do we have something like that? Do we have a strategy profile combination in this matrix where both players will choose?
Yes, sir.
What is that?
Player 1, upper level, and player 2, middle.
Up and middle. Because why? Here we can see both players choosing it, depending on their own strategy, looking into maximizing the utilities, and anyhow, finally, both end up with this option. This is what we call Nash equilibrium. This is what we call Nash equilibrium. Right? So once we have both players end up with a kind of position, a kind of strategy profile, that is what we call Nash. So the Nash equilibrium for this game going to be up and middle. So how we will say it? Usually say your strategy profile using these choices available. So then what will not 1 and 2, so we will not say in that way. So we will say the strategy up and middle. So up for player 1. So first we will say player 1 strategy. So up for player 1 and middle for player 2. So then our strategy profile going to be up and middle. So you can use a comma simply to show your strategy profile. Even you can say it this way, right? Using set theory simply. Anyhow, it is going to be a subject of all. So we discussed this simple SI, factor SI matter last lecture. So then you know this is going to be a subset of the whole set of strategy profiles and simple SI. So this is the first subset, and this subset obviously the Nash equilibrium set. Right? So this is the Nash equilibrium, which is up and middle. Now you see anyhow we started with few complex things, but anyhow this is the simplest way to recognize Nash equilibrium. Right? This is the simplest way to recognize Nash equilibrium. So now we need to practice this few times, and then you may easily recognize your Nash equilibrium for a given game. Right? Right. So do we have any questions from this? Do you need anything to make, or do you need some, is it more clear? Let me know. Or if you have any concerns, or if you need anything to add here, please let me know. Is it okay?
Clear, sir.
Right. So then we'll go for, to the slides and see this, the processing the summary, and then we will go for more activities. Right. So anyhow, so this is what we did. Right. So after it has to discuss, it's going to be automated, right? And so then this is the process. This is what we obviously did, and so you can see the process in these terms, in these sentences. So first, start by identifying the role player's best response to each strategy of the column player. Right? So you can start first like with that way. So what could be the role players? So you know, I think what the role player, column player matter. So because basically role player means player one in that example, right? So then start by identifying the role player's best responses to each of the column players' possible strategies, and then put a bar underneath the role player's payoff once you have identified the best response. That's what we did, right? And do the same with the column player as well, and put these bars. And once you are done, if some entry of the matrix has 2 bars, that is what we call Nash equilibrium, right? So this is the process. So then if you go through this process, simply you could recognize Nash equilibrium, right? So hope this process is clear to you. If this is not clear, let me know. If this is not clear, let me know. So because we have to strictly familiarize with this simple process. This is what we are using to recognize Nash equilibriums in games. Is it okay for everyone? Is it okay with everyone? So I will move forward, but if you have any concerns, questions, let me know, right? Okay, so here we have another example. Now I need your support, so I'm not going to board for this example because so we'll work here. So I need your support to recognize Nash equilibrium for this example. So can you guide me to identify or to follow the process we just discussed? So we will try to put bars, right? First we'll start from player 1, and what are the best strategies for player 1 once looking into strategies of player 2, right? So if player 2 plays L, what's the best for player 1? So player 1 also got 3 options: T, M, or B. So it's a top, middle, bottom, and for player 2 it's left, center, and right.
E.
Yes.
E.
For player 1, what's the best? B.
No, sir. M. Player 1 M.
Exactly. For player 1, it's M, because player 1 got these 3 options available, right? Because now player 2 plays L, no, left. So then player 1 got these 3, and out of that, middle number 4 going to be the highest payoff, right? So if I didn't you provide specific instructions, always think greater the payoff, greater the number will greater the outcome, greater the utility, right? Right. So once player 2 plays center, so then what's the best outcome for player 1? So we have these 3, this and this now. For player 1 again, whether it is going to be top, middle, or bottom now. Can someone mention?
Top, sir.
Top, obviously. Number 4, right? And if player 2 plays right, So we got this 3 available. What's the best for player 1?
Bottom.
Of course, 6. Right. Now we go to the other player. So now we look into player 2 and what are the decisions of player 2 once player 1 goes for different strategies. So if player 1 plays top, so then what are the options available for player 2? Them are the options. So then what is the best?
L.
Of course, L, because that is 4. And then if player 1 goes for middle, we got these things available. What's the best?
C.
Yes. And then finally, here the best going to be right, isn't it? We got 5, 5 and 6, right? And so finally, where we have the Nash equilibrium?
Player 1 for B and player 2 for R.
Of course, player 1 for B and player 2 is going to be R. So that is what our Nash equilibrium. So then finally, our Nash equilibrium static profile is going to be BR, bottom and right. So we'll say it in that direction. First for player 1 B and then for player 2 R. So our strategy profile is going to be BR, which provides us 6 and 6 degrees, and that will be the equilibrium for players. Right? Okay. This. So there you are. Right? So now you are in the correct path. And we have another game. So now we are moving ahead with few games, right? To make it familiar and to see different dimensions as well. So in this game, so again I need your support. Okay. So in this game, we'll go through the same process and we'll have a special name for this game, the Battle of Sexes. So we'll see why, right? Even that book I mentioned you. So once I upload it there, you can see this story even in a nice way. You can read and see why this problem occurs in that in this case, right? So here I will say the story simply. So we got a husband and wife here, Paul and Alice, and them are having choices. I mean, they are having different choices because of gender. We have different choices, isn't it? So usually men will happy to go for things like fights and so on. If you think of having or watch something in your free time, so then you will go to watch a fight, something like that. But Alice will happy to go for opera, right? So then anyhow, now husband and wife to approach somewhere both together because they have to stay together now, and they are husband and wife. But now they are in a kind of conflict with their decision making process. Now they are in a problem to decide, okay, what we'll do now. So now here Paul got two choices, and even Alice got 2 choices because either opera or fight. Now Paul have to think of Alice, and even Alice have to think of Paul as well, as they are husband and wife as well. So now finally we will see how they will go for their decision. Right? Now in this matrix, when it's on payoffs, you can see the payoffs are given in a special way. So we have things given, and then first we'll go to the Nash equilibrium process, and later we'll see why we have such kind of payoffs as well. Or even if you go to the story, you may of course recognize why we have this kind of payoffs for this kind of matrices. Let's come to this example. Right? So now here we'll first go through the same process. Okay. So let me know. So how we'll recognize here. So again we'll think the same way. So Paul first. If Alice goes for opera, what's the best for Paul? We have this and this.
Opera, sir. Oh.
Yes, yeah. And then if Alice goes for fight, what's the best for Paul?
Fight.
And the other way, what we have, if Paul goes for opera, what's the best for Alice?
Opera.
Yes. And even if Paul goes for fight, the best will be here, isn't it? For Alice. Fight.
So finally they will end up with these decisions, as always they are deviating from zeros. Right? And now what we can see here. What we can see here.
Multiple Nash equilibrium.
Exactly. So now here we have two Nash equilibriums. We have one here and one here. Now, unlike previous examples, here we got two Nash equilibriums. We got two Nash equilibriums. Now, what is going on here? So now you may think, so this all happened because of the way we put these numbers. So reason behind these numbers, payoffs given in that book with the story. Please read it, and then you will recognize why. Right? Why they always thought of, I mean, this way kind of providing these utilities. That's how usually once we have this husband and wife problem, so they will go for decisions in that way. So you can read the whole story there, and you can have clear idea about the way why put numbers in this way. But anyhow, now technically, if we use the same process for Nash equilibria, we have multiple Nash equilibria. We have multiple Nash equilibria. So then it means when we have situations with multiple Nash equilibria, then we have situations with multiple Nash equilibria. Okay. And so yeah, this is what. So now we almost discussed it. Now then, out of this, if you ask to go for the most reasonable prediction, right? So then, having two Nash equilibria, if someone asks you, then please go further and see. Then finally, what the best anyhow, where they have to go for their fun. So because now here seems like opera, fight, both are having equilibria, but they can't go both play same time now. So then what will be the most reasonable prediction? For that, how we'll do something. So I will show it soon after few things. At the end, I will show you how we can think further. And for that, what we need, something we discussed last session, mixed strategies. Right? So we have to go for mixed strategies. Finally, to choose one from these two if we have multiple Nash equilibriums like this. Okay. Now we have another example. So let me clear these things first. Right. So here what we can see, so we call this matching pennies game. So I mean here coins, so you have to put a coin up and then you will get either head and tail. So then both players will flip a coin and record the outcome, something like that is happening. And then here we given the outcomes. So if you get head, you get 1, otherwise -1, likewise the utility is recorded. Right? So in this example, if you try to find Nash equilibria, you may not find the Nash equilibria. So we'll see. Right? Now having player 2 playing H and T. So for H, this will be 1. Isn't it? This will be 1 for player 1. Having player 2 playing tail, this will be here this one. Right? Likewise, if player 1 plays head, the this will be tail for player 2. And even having player 1 plays tail, this will be here for player 2. So now in this game, we couldn't see any Nash equilibria. So we have situations like that as well. We have situations like that as well. Right? So this is what we call non-existence of Nash equilibrium. Right? No pure strategy Nash equilibrium. So then even once we got such a situation, right? Further we can again think of mixed strategies to find out an ultimate final outcome of a choice. Again we can get the support from mixed strategies to recognize, so then out of then this complex situation, what could be the possible best. Okay. Right. And with that, let me give you a challenge. If I am correct, even I show you this, I don't know, I discussed this earlier as well. So can someone here prove 1 equals 2? Can someone prove 1 equals 2? Do you think it's possible?
It's possible.
It's possible.
I think earlier also we have seen 0 equal 1 or something in previous lecture.
Yeah. So then, so what's the problem with that proof? Can you remember? Yes, we can prove that 1 equals 2. And what was the problem with that proof? Could you remember? Okay, let me go through that proof soon and then please show me what the problem, right? Now you all know that there's a problem now. So you need to recognize problem of that proof now. Right. So what we'll do, we'll try to prove 1 equals 2. For that, let me say a equals b, because so I'm let this variable equals b. So we have to do this. We can say a equals b, and then so let me first do something. Now we got two variables a and b, right? And now let me multiply a equals b from a. Then what will got? So what will be the outcome?
A squared.
Yeah, maybe. Okay. And now let me subtract b squared from this, both of these. Okay. Now when it's come to here, we got this what we call factorization. You could remember, right? So we have a minus b square terms. It means a minus b, a plus b, isn't it? Could you remember?
Yes, sir.
Here we got b. We can take b out as we have b, and then we can write it a minus b. Okay, and then I can then divide both sides from a minus b. So then this will be cancelled out. So I have a plus b equals b, and then since a equals b, so I can write it this way as a b plus b equals b, which means 2b equals b. If I divide both whole from b, because just we can divide by as and b, then finally this will be what? 2 equals 1. So okay, 1 equals 2 or 2 equals 1, the same thing. So now I am here with the proof to say that 1 equal to. Now you need to show me problems here. What's the problem? What's the problem in this proof? You can go through it and see.
Can we cut this a minus b and a minus b?
Why? Here? Why? What's the concern? Because a minus b, no, both sides we can divide mathematically. So can you specify? Why you say can we cut? Okay, so of course let me say yes, there's a problem with this cancellation. But what is the problem? It's not about cancellation because we can cancel. But there's another problem. What is that problem? So think where we start. A equals b, right? If a equals b, so for here even I can say then a equals a, no, because a equals b, no, right? So
So then A equals A means what? 0. So can I divide anything from 0? So if I divide anything from 0, what will be the outcome? The same thing applies here as well. So it's going to be 0 as A equal B. So if I divide something from 0, what will be the outcome?
Infinity.
Of course, again, we are end up with infinity. Here, we are end up with something problematic again, right? Again, infinity. Now, always we are having this infinity, isn't it? Anyhow, so you see, we have a problem, right? But the proof seems like very nice. But you see this element, and you have to cross check it very carefully, right? So why I did it? Because when it's come to game theory and most of these behavioral approaches with the numeric applications, even with the proof, we have to make sure the meaning is there. We have to do it in the meaningful way, and also even the proof and then practicability and even the practical nature of that. Right? Now I am not going to discuss the problems with Nash equilibria or the game theory in detail here, right? But Nash equilibria even have some problems, but we are not going to discuss them in detail. But when it comes to anything, a proof and so on, again we have to see whether they go through. I mean, there's no mathematical error with Nash equilibria, but there's a practical error with Nash equilibria sometimes, and later on some people elaborate it and show that Nash equilibria are not always the truth when it's for decision making. But now, it's not say always Nash equilibria false. No, even Nash equilibria also got some extensions. Right? Some situations are not mentioned with Nash equilibria. So then there are some people who develop more theories and find it more Nobel prizes also. Right? Anyhow, now here what we will keep in our mind, in any process there will be error, though it shows very nicely. And because of that error, there will be the whole thing will be a falsification. The whole thing will be just something which is not useful at the end. So because of that, always be careful once we go with mathematical applications in any of your work, maybe in your research project or maybe applications in game theory and so on. Always think whether the meaning is there also. Always check whether the meaning is there with your application. That is really important, right? Okay, because why I am saying it, now we are going for bit another step forward and bit advanced applications, and there is really important to understand the meaning of what we are doing. Otherwise, we'll end up with a lot of problems. That's why I want to say that, and then with that we'll move forward for the next part. And in that part, we'll do some, I mean, not that much of advanced, but we'll do few advanced applications and see what we can do. Right? So we'll call it Nash equilibrium clarifications and examples, right? Now again I will come back to board, and then I will show you this matter, and then we'll discuss. I mean, here first we'll go for that what we call battle of sexes example, and there we'll see having two Nash equilibriums. So then, how will we recognize the optimal choice out of multiple Nash equilibriums? So that is what first we are going to do, right? And we'll see what we can see there. So first we go for that, and let me again emphasize. I mean, make the board full screen. Till that, let me know if you have any problems, and even now. This Friday we are going to have our last session, and in that session I am going to give you the next quiz, right? I am going to give you the next quiz, and this next quiz will come from 3 sessions. I mean this session and even the previous session and even the session before. I mean, so then you have to go through decision making on uncertainty, or even 4 sessions: utility theory, decision making on the uncertainty and expected utility. That's the second session, and game theory 1, game theory 2. there are 4 sessions. So my quiz will pop out through that 4 sessions, right? So then you have to get ready with that 4 sessions by this Friday, 10 o'clock, as I'm giving you a quiz at the beginning of the session. Make sure to be there and make sure to go through these 4 sessions, including the session today. And it is very important because this is the second quiz, because we are doing only 2 quizzes, and the second quiz, do not miss out it, right? Okay. So we'll try out previous example. If you would remember this husbands and wives problem, opera and fight matter, right? So let me say this Paul, Alice here. So we put A, Alice, right? And this is what we got. Okay, so now even we recognize that we have multiple Nash equilibria in this game. Both of them are multiple, I mean Nash equilibria. Now the challenge for us to find out then what will be their decision at the end, because they cannot the same time both of them cannot go to both places. Right, so then they have to find one out of these 2, and again, so then now how will they will go for this decision? Now for this one, we are going to mixing up strategies even and see what's the possibility. So then we are going to deal with what we call the mixed strategies, right? So far what we did all only from pure strategies. That's why we call them also pure strategy Nash equilibriums, right? So each player got 2 pure strategies, opera or fight, opera or fight. But now we are going to deal with mixed strategies and see what we can do, right? So now to make it, I mean, more clear, so let me use some symbols to represent each of situations, right? So now here let me say the probabilities, right? If you say in this way, if the probability of going for opera and fight for Paul represent from y and y minus 1. Oh, let me say x 1 minus x, right? Yeah. So x will be the probability for going opera, and then obviously the probability for going fight will be 1 minus x, because finally the addition of these 2 should be 1, because we know probability will be 1 and finally, right? So then if the probability of going to opera is x, and then 1 minus x will be the rest of the probability for the other option. So then we'll apply the same thing for Alice as well. We'll put letters y and 1 minus y. Okay. Okay. So this is the initial state. So we provide a notation for probabilities, and knowing that addition of this probability is going to be 1 always for each couple of choices available. Right? Is it clear? Now if we think of strategy mix, if you think of Paul and Paul's strategy mix, Paul going to mix their strategies in between these 2 now, because he got 2 pure strategies, and then Paul can mix up these 2 pure strategies. That's what Paul can do, right? We got 2 pure strategies and we can mix up these 2 pure strategies. Now we will see how we can mix up. That is very important. Right? Now once we think of this, we have to do a simple calculation. Right? And we'll see this calculation, and we'll even try to understand the meaning of that calculation as well. Right? Now, so now for Paul, now we'll think it in this way. So this is how these are the pure strategies that Paul can mix up. And then for Paul to indifferent between Alice's choices, or indifferent between his choices, right? What we need to have. So Alice got chances of y and 1 minus 1 with her choices. Paul got chances of x and y minus x with his choices. Right? And now what we need for Paul to be indifferent in between his choices, what's going to be the formula? So we are trying to develop a simple formula for that using the idea of mixed strategies. And for that, let me say it in this way. What is this? So how we get it? So here what we'll do, we'll see Paul's outcomes, right? So here Paul got two outcomes, and in these two outcomes, this is the best outcome, right? Paul got two outcomes. This is the best outcome in terms of its probability. That's why we are going this direction, right? In terms of probability, this is the best outcome. So now what we'll do, so then we'll apply this one with her formula, her probability. So 1 with her probability. So that is what we can see here. That's the meaning of y here. The gain, the possible gain out of this choice, the best possible gain is 1 for Paul out of these two, and then we'll multiply it from y, that is the probability, right? And then here we have again two options, right? And then best will be 2. So then we'll multiply 2. Even now here, let me say, here even we can do the same thing for other part also, but we'll end up with 0. That's also there, right? So even you can extend this like this: 1 into y plus 0 into y equals 0 into 1 minus y plus 2 into 1 minus 1. So to make it more democratic, so we can write it this way, because now we are applying for everything now. Right? We are applying for each option. So Paul got two options, and for with the probability of y for Alice, right? So that is what we apply. So then 1 into y plus 0 into y. So this will be 0, and 0 into 1 minus 1, 0. Luckily it's about addition, not multiplication. So then this will be go out. This will be go out, and finally we have 1 into y is y equals, we have 2 into 1 minus y. So this is the formula for Paul's decision making process. You say. First, can we try the same thing for Alice? Can you think of it? Now, how will apply the same thing for Alice? The same procedure to Alice. Can we do it? So, shall we follow the same procedure and see whether we can do it? Now, we will think of Alice. Alice also got two options, and now the probability is here. No, so the other way around shall be this 2. This 2, this and this, and this. Am I correct?
2x equal 2 into 1 minus x.
Yeah. So then here we got x and 1 minus x. So then zeros even you can use, right? So then 2 into x, 2x plus 0 equals, here we got how much? 0, 0 into 1 minus x plus here 2 into 1 minus x. Am I correct?
Yes, sir.
So then finally is it 2x equals 2 minus 2x. 2 minus 2x. Is that so? Or without simplifying, we put it in the brackets. We return. Earlier also we did simplify now. Minus x. Right. So then this is for Alice. So why we derive this two? Now the next step going to be the decision making process. So now we got formula for both having the probabilities. So for probabilities, obviously we put this notation and we generate a formula. If you get the correct probability, so we can calculate this, right?
Excuse me, sir. Sir.
Yeah. Mhm.
In 1 minus x, is it 1 or 2, sir? Because I think 0 and 1, there we can go with the 1, no, sir. 2x equal, is it 2 minus 2 into 1 minus x or 1 into 1 minus x?
Here.
Yes, sir. The 2x is okay, sir. When
Mhm.
there's a 2 and 0, we can go with the 2.
Yeah, of course. Yeah, here it should be one. You see, this one we have to consider,
Yes, sir, yes.
not this one. Exactly. Great. That is what. This is the payoff now. Like what? This is the payoff, not this one. Exactly. This should be one. 1 into 1 minus x, and finally then it's about 1 minus x, right? What about others? Do you get it? Because this is not about Alice, this is about all. So we don't need to mix up it. Now you all, I think, get the point. So always think of the correct meaning matching up, and then here it should be 1 because it's about Alice. Alice payoff should be here, not someone else's payoff. So then we obviously multiply 1 from 1 minus x and we get 1 minus x. So now formula will be 1 y equals 2 into 1 minus y, and 2x equals 1 minus x, not 2x equals 2 into 1 minus x. Right? Okay. So what could be the next step? What we'll do next? Now what we'll do, can we try to solve for some here? Can we find a answer for this formula? Can we find the answer for this formula? Is it possible?
X equal 1 divided by 3.
Yeah, if you divide this, if you simplify this, what will you finally get? X equals 1 over 3. So simply you have to simplify this formula, then you get x equals 1 over 3. Right? What means x equal 1 over 3? What do you think? What could be x equal 1 over 3?
So here we have the two choices. I
Yeah.
think if
No,
we
it's
go
about-
with the 3, then this problem may be settled.
3 means?
So here we have only the 2, no, so 2 choices. But
So-
according to this, yeah.
So let me use this part of the board. So I'll just remove that, but we have this formula, right? Now when it's come to, it's 1 minus x, and the are the probability mixes now, I mean available probabilities for each choice, right? So then, yes, Vijay, you can continue what you say till I clear this and put some notations.
So I thought in last week also we looked at there's a 3 choices. So it
Yes, example. Yes.
yeah in there also 1 divided by 3. So here but we have the 2 choices only for both players.
Mhm.
I think if we go with the 1 divided by 3, there may be a chance to settle this multiple mass equilibria. We can solve. I think I don't know.
Okay. So now anyhow this x equals 1 over 3 means this, isn't it? This is the value for x, no?
Yes, sir, yeah.
Here we got x, this is the value for x. That means this is 1 over 3. And 1 minus x means then 1 minus 1 over 3. Isn't it? It means 1 over 3 and 1 minus 1 over 3 is 2 over 3. What do you think about this? Because this will be 3 over 3, then 3 minus 1 will be 2. So then we get this. This is going to be the probability mix. The probabilities that you can mix. Finally, the addition of this also equals 1. 3 over 2 plus 3 over 1 equal 1. And this is your probability mix, and which reflects your mix strategy. This reflects your mix strategy. Now, even for Paul, even for the other player, we can go for, even for Alice, we can go for. So then for Y, we have the solution. Can you go for the solution? For this one? What is the solution for here? Can you try? So it's then we have 2 minus 2y. 3y equals 2 divided by 3.
2 divided by 3.
2 divided by 3. So then we'll apply the same here. So y equals 2 divided by 3 and 1 minus 2 divided by 3. It means we got here, so 3 over 3, 3 to 1, 1 over 3. So this is the probability mix for the other player, for Alice. Right, so then throughout this process, now we are getting their mixed strategy profiles. So them are the mixed strategies. The way they can combine, the way they can go for their mixed strategies. Right? And so then, finally, what we can say is, so let me say it in this way. Here we say Paul mixing what? This one, and is mixing this one. Am I correct? And then as a result, 1 over 3, 2 over 3, and 2 over 3, 1 over 3. This is your mixed strategy Nash equilibrium. This is our mixed strategy Nash equilibrium. So why we are saying this is our mixed strategy Nash equilibrium? Because we start from here and we observe what's the best possible response for the other player once referring to their probability distribution. So here we got this one, and then we saw their end nodes, their outcomes, and we multiply them with the formula, and finally we got these things. And then this is what obviously the best outcomes for each player for the given situation while mixing up their probabilities. So this is the probability mix, and that probabilities are their mixed strategy Nash. So then if you ask to go for a mixed strategy Nash equilibrium, so this is the way you can go for it. So then this is going to be your set of mixed strategy Nash equilibriums. Right? And even we can go further. If we go further, Now we can rule out one mixed strategy natural equilibrium given from here, but we are not going for that extent. But anyhow, this package will be the mixed strategy natural equilibrium for this problem. Right? In the discussion, we will go for another example with another mixed strategy. So then you will get more clear idea. Right? Now, so do you have any questions for this one? I mean, any concerns? If not, I can. I mean, maybe you have concerns. But to make clear that, I will go for another example soon. And so we can extend the discussion on this example in our discussion as well. And then there I will show how again we can go for another mixed strategy natural equilibrium. I mean, a kind of another mixed strategy solution also. So this problem going to be a more, I mean, applied type of problem. This is a term called shirk or avoid working. The term will represent avoid working or work here. So this player will be, let's say, A for agent, here P for principal or the employee. I mean employee, employer, the same idea, right? This is the person who is working in a company. This is the person who is supervising him or the boss of this person. Now what I will tell this a story here. So we got a person working who do his or her job in the industry. This person, and this is the person who is supervising him, right? So then we will say the leader or manager, right? Now this person at work can either avoid working or can work well, right? So here strict means he can just do things but not in the proper way. He can keep working properly and so on. Work means do their job properly. And what this player can do, I mean this principal can do, he can either inspect or stay without any inspection about this person. Right? So inspection means so you will observe some other things, whether this person working or not. Or here means you will not care, you will not look in seriously whether that person working or not. Right? So that is what we can see here. So now let me show you outcomes. So I will explain what are these things. Here they are given in a kind of formula way. This is B minus W minus H. So this is the demand payouts. Now them are not in numerical format because now anyhow you may feel even now we are going for another. We are reaching again back to some complexities, but we'll see what we can see here, right? So here I will give you an introduction for this payouts, right? So I will read this problem for you because you can see it here. So I will share the screen and then I will first show it to you and then later we can discuss it. So I will share this document later on. Here also the thing we discussed in here. Yeah, this is one. Okay. So it says, consider the following game. An agent works for principal, right? The agent can shirk or what means avoid or work. Working cost the agent G. So here this G means the cost that the agent or the person who is working will get because of working there. So working cost the agent G and produces output of value B. So if you work there, so you produce output of value B. This is given here. Right?
So value will be created for the principal. So you work there and your value will added for the principal because they will finally end up with the outcome. And inspection costs the principal H. So if you inspect this person is working, that will cost you H. The principal pays the agent W, that's the wage, right? Unless he has evidence that the agent did not work. So usually what will happen, the agent, the owner will pay W amount of salary for this person. Assume that W wage greater than G means cost of the agent, and which is greater than H means the cost of inspection, and which is greater than 0. Right? So this is that's what given as information. Right. So now, can you recognize what we have? I mean, can you go through this example and now try to see the combinations of outputs given here and the meaning of them? So now it's really important to recognize the meaning of these letters given in these boxes, right? So now we'll try to recognize the meaning of these letters. So 0 means okay, nothing. 0 means 0, and minus H means then. Now then 0 will be what? So what is the meaning of this? If the worker avoid working and if principal inspect that, the principal here, the owner inspecting, then you will be not pay anything and you will fire out of the job, you will get nothing. So then for the agent, you will end up with 0. That's the idea here. And the same time, H means what? The cost of inspection. So then since you are inspecting the agent, so you have a cost of inspection given in minus H as a cost. That is the cost given in minus H. And now if principal or if owner is not inspecting, so then this agent will get his wage, but anyhow this wage is going to be a cost for the owner, because why? This person is not working now, so this is going to be a cost. Anyhow, no additional outcome, no value added, but the cost is going to be, the wage is going to be a cost. Right? And for the agent, if agent work without avoiding anything or properly work, so then obviously though inspect, so then principal see this person works well, so then give the salary. Anyhow, because of working, this is the cost of working. Maybe you have to put effort and so on. This cost of effort and so on will be G, and then W minus G going to be your finally your gain, wage minus cost of work for the worker, and then for the principal, for the manager. So you have value added. And then so even here it's better to note. So I forgot to say here. Even so, finally value added will be greater than wage as well. So then your production of the value added minus wage minus H. Which means the cost of inspection as you are inspecting. So then this will be the cost for owner. And then the next option, if the owner is not inspecting, so anyhow the same thing applies for the agent as he is working and the cost of working subtract by the wage. Anyhow, there's an advantage for principal, the owner, because right now there's no cost of inspection. So this is just about the wage as the cost. The rest will be this profit or whatever. So this is the matrix. So do you get what's within this matrix? Is it clear with you all, or do you have any concerns about that? Is it clear?
Since it is not in numeric value, it's
Yeah. So I said,
yeah.
because things can come in this way as well. But do not worry. So this is not in numeric value, but the same idea here, depending on the story. Now here is really important to add the meaning to these terms, and then only we can recognize. So we have 0. So where you got problem? Can you say? Where are you confused? Show me the combination. Now, even do not worry, right? So it's about, I mean, kind of letters which added together represent the payoff finally. The same approach, but now we are having few letters with their own meanings. And to show cost, always we put this minus sign and it's lemma cost. And for gains, we show them as positive. So there's no specific sign for that. So please, others can even raise your voices and tell me. So if you need further instructions on this game. Okay, so let me move ahead and we'll see. So, but once I move ahead, if anything is not clear, so we'll come back here and we'll again try to to try to simplify the explanation. Okay. Now, here what we have three questions. Now, question number 1 would ask, show that there exists no pure strategy Nash equilibrium. So now we have to identify the Nash equilibrium here. Now here we have it's be different because why? Now there's no numbers, but we have some expressions. Now it's really important to recognize the meaning. So this is why I said about the meaning, the importance of meaning in any expressions, numeric and formulas and so on, right? And now we are going to practice it. So now we are going to apply the same procedure. So now you all know the procedure of identifying the Nash equilibrium, right? But for this, now how we can do it? Can we try?
So here we don't have the Nash equilibrium, no, sir.
Don't we have? Why? So can we try out it? So we'll see the best options. So now for first for agent, if principal inspect, what's the best outcome? What's the best strategy? If principal inspecting, looking whether you are working or not, then obviously best strategy will be working. Because why? Otherwise you will fire out from the job and you will get 0. Isn't it? So then the best strategy will be working. So you will get the wage and any of the cost will be less than wage now. So you will get something. You will get your wage, the net wage, but here you will get 0. So because of that, the best strategy will be working if the principal inspecting. If the principal not inspecting,
Working.
not working means what? Are you sure? If the principal not inspecting, what's the best strategy? This one, isn't it? Avoiding work, because why? Here you get W, here you have W minus G. So here you get wage but not without cost because you are not working now. So then you don't need any effort. You are just staying there while chatting with others. You are not working. So then you are earning without any effort. Isn't it? That's the best law for you. It's not good, but that's the best in terms of financial gain now. Without any effort, if you can get anything, but that's why people going across lotteries, right? Isn't it? To get
Yes, sir.
things. Yes.
So I also thought this one, sir. I thought W means working. I also so,
Okay,
yeah.
okay. So please always provide your decision with the option available, right? Because of 2 W's, isn't it? You thought of that. Yeah. Working will be the option. Here it's the wage, not working. And this W says working and this strict, so this avoiding work will be option, which will give you wage. So this W inside this matrix, which is about wage, right? Salary, not working. Working is an option for agent. Working or not working. S means not working. W means working. All W's inside the boxes are the salary, wage. Okay, right. So then now for the principal, if agent not working, what's the best option?
Inspection.
Inspection. Why? We know here H is lower than W. So the lowest cost will be cost of inspection rather cost from someone who's working without anything. So then finally, you better go for this. Right? So inspection will be, this will be your best outcome. Right? Cost of inspection. And then if the agent working,
No inspection.
no inspection. Yeah, you are now practically you can give the answer, isn't it? Now you are practically you may recognize this what the best, and even from here you can see the same application with these terms as well. So then if agent works, so then okay, so this will be not inflation, then that person is working. So that's the most advantageous thing because cost is lower than the cost here because you don't have inspection cost. Right. Then of course, I think what you mentioned is correct. Like the points situation, here even we don't have a Nash equilibrium. We don't have a Nash equilibrium. Why? In different situations, their desired choices are different. There's no position where both desired choices are getting together. So no Nash equilibrium in this situation. Okay. So then, so from here I will stop, and then there will be another part for this question. That is what. So you want to check whether we have mixed strategy Nash equilibrium. So then in the discussion we discuss. Okay, so then having this situation, how we can go for a mixed strategy Nash equilibrium. So make sure to attend the discussion because it's really important. So because we are going to discuss again about the mixed strategy application for this one. Right? Please attend the discussion to discuss that. Okay, so with that, I am going to wind up the session today, and so let me thank you all for attending the session today. And if you have any concerns and all, feel free to contact me as well. Because now by this Friday we are going to have the quiz as well from last 4 sessions. So I almost upload the slides and videos for previous 2 sessions, and for game theory sessions I will upload videos by tomorrow morning. So then you can access both of game theory sessions as well, the day one and the previous one, and then go through them and get ready for the quiz. And we will see when Thursday come up with your problems to discuss regarding these 4 lessons, and then you can clarify them before going to the quiz. So then this Thursday we'll discuss more about these things, and then with that mixed strategy application, and then finally in the Friday by 10 o'clock you will get the quiz, and even will then go through the next lesson, the final lesson for this series, information economics. Right. So thank you, thanks a lot, and stay safe. And feel free to go through all lecture materials and get ready even for your exam now. Exams even approaching now, so then get ready from the as well. Right.
Sir,
Yes.
a small request, not the request, doubt, whether we have the multiple choice questions or the written ones for quiz.
So the question is going to be multiple choice because I mentioned it earlier. Is given it, isn't it? You may do things from yourself. Finally, you have to go for multiple choice question. I mean, you have to find the answer from multiple choice problems.
Okay, sir. Okay, thank you.
Then finally, to get your answer, you have to do a few things from your own. I mean, the answer will not clearly visible. So then you have to do some things and so on. Finally, get the answer. Okay.
Okay, sir. Thank you.
So quiz will be an online quiz, and as we did last. So then by that time the quiz will appear, and then you have to attend it. The quiz will be basically, so last time even we had this Moodle method, right, for quizzes. So the same method will apply for them. So then so in the Moodle, so you have to accept the quiz and you have to go for your selection. And this selection process, for that you may need papers and pencils and whatever to do this calculation from your side. That's all. Whatever calculations or whatever things. Okay, so that's all. So if you have any other questions, then please let me know. And if we don't have more questions, so then you can feel free to leave. And I will wind up the session.